We did Euler's method with 2 steps. We came up with 3.56. I showed you that linearization is like Euler's method with 1 step. Of course, the step size would be 0.8. We got 3.4. 3.56 should be a little bit more accurate. We're going to find out how accurate because on part B, no space, solve the differential equation dy dx equals x minus 2 with the initial condition 0.5, and then use it to find the actual value of y of 0.8. Okay, so step 1, separate the variables, right? This one's pretty easy. dy equals x minus 2 dx. If you do it like that, how you doing? Yeah, you would need parentheses. Good. Yeah. So there would be the separation check. Integrate both sides, and of course you get y equals 1/2 x squared minus 2x plus c. There's your general solution. So at the point 0.5, make sure you're indicating that you're plugging in. At 0.5, you get 5 equals c. Hey! So, a great transitional word. Y equals 1/2 x squared minus 2x plus 5. There is your particular solution. And now we can actually calculate what y of 0.8 actually is. And again, we communicate it in function notation with y of 0.8. You don't have to say at x equals 0.8. You get 1/2 times 0.8 squared. 0.8 squared is 0.64 minus 1.6 when you double it plus 5. So that's going to give you 0.32. That's going to be plus $3.40. So it's going to end up being 3. Is that right? 0.72? Any confirmations of that? Yeah, that looks good. So let's compare the values we found above. Of course, the linearization, the 1 step, the tangent line approximation, 3.4, you're off by about 32 hundredths. Not so bad, perhaps. We're straying 0.8 of a unit away. But notice Euler's method is 3.56, which is a little bit closer to 3.72. And that was only taking 1 extra step. Again, the beauty of Euler's method is not just that it uses lines still, but that you can take more steps if you need to be more accurate. And because it's such a systematic approach, calculators can do it. Computers can be programmed to do it. And I'm going to show you on the next one, there's several programs online that you can find that will do this for you for hundreds of steps, which you're not going to have to do unless the phone is not ringing on a Friday night. Okay? Then it does help pass the time, and as Rap can testify, it does make you feel better, right? Math is good medicine. Yeah. Chicken noodle soup for the mind. All right, example 2. We're going to do this one together. If dy dx equals 2x minus y, notice you're given a differential equation in terms of x and y. And if y is 3 when x is 2, there's your starting value. Use Euler's method with 5 equal steps. Holy moly, that's a lot of steps, relatively speaking, to approximate y when x equals 1.5. All right, step 1, what method are we going to use? Yeah, it says Euler's. There it is. Okay. Step 2, you need to figure out delta x. We are starting at x equals 2, and we're going to x equals 1.5. What's most noticeable about that? It's going to the left. So your delta x is going to have to be negative. So if you want to figure out what delta x is just by routine, it's your ending point, which is 1.5, minus your starting point of 2 over the number of steps you're taking of equal length, which is 5. So 0.1 negative, right? Negative 0.1 or negative 1/10. For Euler's method, maybe you're more comfortable working with decimals. Now, for a problem like this, with 5 steps, the numbers do get tedious. If you would like to use your calculator to help you with your calculations, feel free if you have it. The columns are x, y. That one's pretty easy, x and y. What comes next in our table? M, the slope that you calculate. Once you have the slope, what comes next? Delta y, which is the slope you just calculated times delta x, which we already know. And then if you want, on this last column here, put y sub nu, or you can go ahead and just put the new y value in the second column on the next row. I like to have that last column there. Okay, so we're starting with x equals 2 and y equals 3. And the slope requires both x and y. So what's the slope at 2, 3? Well, it's 4 minus 1, which is 1. Nice. So we're going to walk out along that slope a little bit, and our delta x is negative 0.1. So what's negative 0.1 times 1? Negative 0.1. So our new y value is 2.9. Now the new x value, you have to keep generating that. You have to keep adding delta x. In this case, we're going to keep subtracting 0.1. So 2 minus 0.1 is 1.9. And then I'll bring that new y value over, and I got 2.9. So now we're standing at the point 1.9, 2.9, and we do it again. Now here's where the calculator can be really, really helpful. And whether you want to watch up here with me or not, that's fine. I'm going to go ahead and do something here. I'm going to store my delta x, negative 0.1. I'm going to store it as x just to save some keystrokes. All right, so to find the slope at 1.9, 2.9, it's 2 times 1.9 minus 2.9. In a problem like this, you would have your calculator to help you. 0.9, okay, reasonable. And now if I multiply that by 0.1, I get negative 0.09. And if I take that number, negative 0.09, and I add it to 2.9, which was my previous y value, you're going to get 2.81, which is your new y value. So you can add that on the next row, and your new x value is 1.8. And we do it again. Okay, so it gets pretty routine here now. So 2 times 1.8 minus, I can just hit the answer, recall it, it's 0.79, bless you. And if you multiply that by negative 0.1, which I stored as x and I'm not using it, negative 0.079. If you add that back to 2.81, you get 2.731. If you find that your values are changing too dramatically, whether it's your slope or your y values, you're probably hitting the wrong key. So it's very tedious, and that's about all. It's not necessarily very difficult. 1.7 then, you bring it around 2.731, and we do it again. 2 times 1.7 minus the answer, which is still sitting there, and you got 0.669. And then you multiply that times negative 0.1, negative 0.0669. You add that right back to 2.731. And hopefully at this point, if you're doing the calculations on your own, you're getting the hang of it. Almost to the point that you're kind of losing track of what you're doing, which means you can make a careless mistake. So don't do that. 2.6641. 2 times 1.6 minus the answer, 0.5359, and that should be negative 0.05359. So I'll use my x that I stored here for a time saver finally. And if you add that back to 2.6641, you get 2.61051, which when you bring it back around, you're at 1.5, 2.61051. That's where you stop. Don't go another iteration. You wanted to get to 1.5, you're staring at 1.5 comma something, and so now you box it and walk away? No, now you actually write the sentence. You'll say y of 1.5, what comes next? Equals? Squiggles, is approximately 2.61051. Would there be a way to determine if that's an over or an under approximation? Would the concavity still work here? Yeah, you would just have to show that the second derivative would be either concave up or concave down over the entire region that we're working with. You want to attempt that? Let's try it. D squared y over dx squared would be 2 minus dy dx, which would equal 2 minus 2x plus y. Now we're spanning from 2 to 1.5, and notice what our y values are spanning. They're about between 3 and 2.5. Is that going to be so obvious? If I plug in an x value that's between 2 and 1.5, I'm going to be either subtracting a 4 or 3.5. And the y values, the smallest are going to be is 2.5 plus 2 is 4. So it looks like the sum of 2 and y should be greater than the product of 2 and x. Yeah? And so in the region that we're working with, this looks like it could be positive, which means our graph would be concave up, so the tangent lines are below, and it looks like it what might be an under approximation. Yeah, that one's not as obvious. So Euler's method is an under approximation. Now, here's what we can do. We can go to the internet and a real quick typing in on Google or Bing or Alta Vista or whatever you use of Euler's calculator. This was the first link that it came up. You could type in the differential equation 2x minus y, starting at the point 2,3, going to 1.5. It could do 500 iterations for you, which is quite a few. So execute, instead of calculate. We'll execute it. And then notice it shows all the steps. Well, it will notice. There you go. It shows all the steps. So if we scroll down all the way to the last 1.5, whoa. Notice it comes out to 2.648. That one should be a lot more accurate than ours, right? Ours was 2.61, so it does appear that ours is a little too small. So it worked, right? Now notice between the 499th iteration and the 500th iteration, 2.6486, 2.6483. So it looks like the answer should be probably 2.648 if we had to guess maybe what the first 3 decimals were of the actual answer. And using 5 steps, we were 6.1051. If we wanted to get more accurate than this, of course, more steps. That's what's nice about Euler's method. Linear calculations, as accurate as we want to be, programmable. Pretty nice. All right, so far so good. Questions on Euler's method? If you look up here, or down here, below the chart, here's what you'll find Euler's method listed in any textbook. It's that right there. Look at those delicious looking equations. Yeah. The table that I give you is just a way to systematically do that. Okay? Makes it kind of fun. Kind of. Yeah, you're not going to necessarily have to sketch it. The reason I had you kind of sketch it is just so that you kind of get a feel for what we're doing. The function looks like that, and we're doing this, and then we're doing that, and then we're doing that, and we're inching closer and closer to something instead of just going straight out to here necessarily. And so I just want you to kind of get the idea of why Euler's method works. It basically recalculates and hugs the curve, which minimizes the error. Okay, what other types of questions? Well, let's look at example 3. Assume that f and f prime have the values given in the table. Use Euler's method, there it is, with 2 equal steps to approximate the value of f of 2.6. So a slightly different way to give you information. Notice you have a row of x's, you have the next row of derivatives, and then finally the last row is your function values. So the slopes are already calculated. If you would like to make your table here as well, it's a good place to do it. X, Y, M, delta Y, and Y sub nu. Now, we are starting at what ordered pair? 3, 2 or 2, 3? 3, 2. Good. 3, 2. What's the slope at 3, 2? 0.4. It's handed to us. So delta y is what? Well, it's delta x times m. What's our delta x if we're going from 3 to 2.6 with 2 equal steps? 0.2. Positive or negative? Negative, right? We're going left again. That's one of the most important things to get straight, okay? Because if delta x is the wrong sign, you're going to be adding when you should be subtracting and vice versa. So what is negative 0.2 times 0.4? Negative 0.08. Good. And then 2 minus 0.08, $2 minus 8 cents leaves you with $1.92. All right, now if we subtract 0.2, we're at 2.8, comma 1.92. What's the slope at 2.8? 0.7 is given to us. Wow, that was convenient. What's 0.7 times negative 0.2? Negative 0.14. Good. $1.92 minus 14 cents leaves $1.78. And then if I subtract another 0.2, I'm at 2.6. And if I bring that $1.78 around, do I do the iteration one more time? No, I am staring at my 2.6 comma y value. What about that 0.9 that's there? Forget about it, right? It's there to distract you. It's there to lure you, to tempt you. Oh, what a siren you are, 0.9. But I have self-control. I know when to stop. Is it right there? I don't do another iteration, but I don't walk away from the problem yet either, do I? No. F of 2.6, say it. Squiggles. 1.78. When you're doing Euler's method, like up here when we did it and we had all these decimals, don't want to round on the intermediate process, do you? Carry as many decimals as you get all the way through. Is there a way to determine if that's an over or an under approximation, just from the information given? No. No, we don't have the equation or any information about the concavity of the function. All right, the last one. Here we go. The table at left gives selected values for the derivative of a function g on the closed interval from -1 to 2. Let's look at it. All right, I got a column of x values and a column of slope values. Nice. If g of 1 equals -2, and Euler's method with a step size of 1.5 is used to approximate g of 2, what's the resulting approximation? It's a multiple choice question. Very nice. Now, in this case, notice, instead of told how many steps to use of equal size, they give you the step size. It's positive 1.5. So that's your delta x. Delta x equals 1.5. We're starting at the point -1, 2. So if you want to do your x, y, m, delta y, which of course equals m times delta x. I like to write that in there for some reason. And then y sub nu. Again, the chart that you make here helps you organize the information that's given, whether it's an equation, a table of values. We are starting at what ordered pair? -1, -2. And our delta x is 1.5. So what's the slope at the point -1, -2? Well, we only need the x value. Apparently it's 2. We get that from the other table. So it's 2. Now delta y is 2 times delta x. What's 2 times 1.5? 3. So your new y value is the old one of -2 plus the change in y, which is 3. So that puts us at 1. Now what's our new x value? -1 plus 1.5? 0.5. And we bring the 1 around. What is the slope at 0.5? Is it 4? That's the next one in the table. No. Man, we're not using a lot of information in this table, but what we need is in there. It's 1. Okay, that's good. There's a lot of tempting things there. Delta y is 1 times delta x. That's 1.5. So your new y value is 2.5. And if you add another 1.5 to 0.5, you get 2. And you bring the new y value around, you get 2.5. Do we do it again? Because the slope at 2 is negative 6. Nope, we are done. We have 2 comma 2.5. We have the answer we need. We just need to write it in the right format. So, comma, g of 2. Say it, Parrish. Squiggles. Squiggles. Thank you. Squiggles. 2.5. And we're done. That's Euler's method. It's an improvement upon linearization. It's not that difficult, a little bit tedious. You won't probably be asked to do it as many as 5 steps, but if the numbers get excruciatingly painful, it might be asked on like a calculator portion. If you could do it for 2 or 3, you got the process down. You could do it for more. All right, we're done. When's the worksheet due? I think it's like 4 or 5 pages. Monday. Practice, practice, practice. It's really about memorizing that chart and being able to produce it very quickly when you need 6 pages. But they're all fun. There's not a single page of the 6 that isn't fun. Cute? Cute and fun.